Okay, so I will now provide the policy gradient theorem, or I'll derive it, and then we're going to use it in a specific, we're going to use it in order to learn a policy, or to converge on a policy. So we'll start by defining the gradient in our J estimation, in our J, in the expected sum of discounted reward for a specific policy. And we can define that as the gradient of the state value at our initial state. And as I said previously, this can be easily extended to a case where the initial state is a distribution over initial states. But for now, for the sake of simplicity, we'll just assume a specific initial state, S0. And of course, using the chain rule, we'll multiply this by the gradient in our function approximator for the policy, our policy approximator. Okay, now the policy approximator, we don't need to derive that. We know that. What is it?
It's a parameterized function, right?
Depending on your approximator, right? If you're using a deep neural network, this is defined using the backprop algorithm. Okay, so this is dependent on the specific approximation that we were using, but we defined this previously for a deep neural network, and it can also be easily defined for a linear approximator or any kind of approximator. But we're not going to care about that, or we're not going to address this now. We'll assume to know that. And we still need to derive the gradient in the state value under the specific policy that we're currently using for our initial state. So we'll start by writing this out as using a Q value, and this is exactly what you asked at the beginning of this topic. Can we define J using a Q value? Yes, here we can write it out. It's just a bit more complex or more involved compared to just writing a J, but it is, we can definitely write it out as a Q function. How do we write it as a Q function? Well, the state value is simply summing over all possible actions that we're going to take and multiplying the probability of taking that action under our current soft policy, pi, for the given state, times the Q value for the specific state action pair, right? Overall action. Moving on, we're using the product rule to break this gradient into two terms. One would be the gradient in the policy times the Q value without the gradient. Actually, I should take this Q and put it probably outside the gradient. So the gradient does not apply on the Q, right? So the gradient is only with respect to the policy, something that we do know about. We know the gradient of our policy, right? Multiplied by the policy with outside of the gradient, multiplied by the gradient of the Q value, right? This is just a product rule where we break down the two functions. Product rule, by the way, if you don't remember it, it's just defined here. Next, so currently we know, so there are many things that we do know here. We assume to know the gradient in our policy, right? For instance, backprop in deep neural network. We assume to know the Q value, for instance, by using sample-based approach to just observe, maybe sample the Q, the sum of discounted reward from a specific state and action pair. We assume to know the current probability of taking a specific action under the specific state. We know the policy that we are using. And we still don't know the gradient in the Q value. We might know the Q value, but we don't know the gradient of the Q value. So let's continue to break this term down. So we'll rewrite the Q value as follows. It's just the probability of arriving at each possible next state multiplied by the immediate reward of seeing that next state. Multiplied by the probability of seeing each one of the possible next state and the probability of seeing the specific immediate reward given the state and action pair that we're taking, multiplied by, well, the immediate reward that we see and the state value of the next state. Okay, so I'm just rewriting the Q value using the state values, or specifically the state values in the next state and the probability of arriving at that next state. And I'm using here the most general form of the transition probability that also includes some distribution, possibly over the rewards. Now, the interesting thing to note here is that the rewards are not a function of the policy. So we can actually ignore the reward. It doesn't matter the distribution over the reward. We can just sum them up in both cases, as they will not affect the gradient in our policy. So I just did that. And now we have something interesting here, where we reach back, we have some kind of a recursion, a recursive form of the definition of the gradient of V, the state value, in some state S, that is dependent on the gradient, on the state value gradient in the next state. Okay, so we can write out this recursive form over many times, right? We can expand the gradient in the next state given the current expansion that we just made, and write it as a function of the gradient in the next state, right, at S prime prime, and so on. And indeed, here's an example where I expanded the gradient of the next state as an expression of the gradient in the next state, right? And we can continue this process, of course, by defining the gradient in the next state as the gradient of the next and so on, right? It's just a recursive function, obviously. So how would this look if we only consider a one-step trajectory? So in the one-step trajectory, it would simply be the gradient in our policy multiplied by the Q value of the current state and the action that we're going to take based on the action distribution in our current policy, plus the probability of arriving at a specific, well, over all possible states in our environment. What is the probability of arriving at that next state in a single time step, right? By moving from state S to that next time step in a single time step, multiplied by the Q value for that next state and the probability of taking the action that might lead us to that next state, right? Multiplied by the probability of arriving at that next state. And we can expand this expression and write it the same expression for two-steps trajectories, right? But now I'm rewriting it in a more general form. So initially we just computed the gradient in our policy times the Q value for the initial state that we are in. But we can also define that as the probability over the entire state space of arriving at a specific state after 0 steps. So this will just be 1. It's a one-hot encoding, right? It will be 1 for our initial state and 0 otherwise, and then multiplied by that this specific term. Again, it will result in just doing this computation for the state that we are in initially, using the one-hot encoding. But in the more general form, the two-step equation just tells us what is the probability of arriving at each state in our state rate after 0 steps, after 1 step, and after 2 steps, and so on, multiplied by this term, which is exactly the one here. And of course, we can just write it in the most general case for k steps, and this can go to infinity. Whoops. What's going on? Okay. Where we iterate over our entire state space and then iterate over all possible time steps in our planning horizon and compute the probability of arriving at the specific, at any state in our state space after k time steps. We'll sum all of these probabilities and then we'll multiply that by the same expression as we discussed previously, which is the Q value over all possible actions multiplied by the gradient in our policy with respect to that specific action. This more intuitively, this means that we update the policy So it will lead us with high likelihood to the best k reachable state. That is the state with the maximal state value. Okay, so how can we still don't have all of these values. We'll have to still break this down a bit further. So we'll just assume that all episodes start from some specific initial state S0. As I said before, we can easily generalize this to a distribution of the initial states, but for now let's just assume a single initial state. And we have the policy gradient expression approximation that we just defined. This is even not an approximation, sorry, this is an exact value, but we'll need to approximate several stuff here. And this stems from the question of how can we evaluate the probability of arriving at any specific state S, after k time steps, but summed over all possible k time steps. And we want to do it for any state. Obviously, this might be problematic to do specifically if we don't know the transition function, right? The transition model. So next we're going to tackle this question. So here we will start using approximation. One way to approximate it is to just count how many times a specific state S for instance, we're trying to evaluate that, was visited in a given episode. So this would be the expected value of this sum of probabilities, right? And we'll denote this value as eta of S. And this will be the sample-based approximation for the probability of visiting S summed over all time steps. So now we can rewrite our policy gradient expression as eta S times, well, the same expression that we've seen before, which is Q of SA over all possible A's times the gradient in the probability of A given our current policy. So now we have, in this expression, everything is known or can easily be approximated. We can count the number, it's easy to count the number of times we visited a specific state S in an episode, and we can sample the Q value, specifically for the state and action that we're actually following. You can just follow them to the end of the episode and we have a good approximation of the Q value, right? Just a single sample, but it's an unbiased approximation of the Q value. And we know the gradient of our policy. For instance, if we use the deep neural network, defined through the backpropagation algorithm. But there is a practical problem with this, where eta S is actually sensitive to the episode length. Right, this makes sense. What is the number of times we're going to visit any specific state which has non-zero probability of being visited? If our episode horizon is infinite, how many times are we expected to visit state S?
Infinite.
Probably an infinite number of times. So, but in any case, probably I'm saying because, okay, there can be specific cases, but this is not the case. But in the general case, we do expect to visit S more often if our episode length is longer, right? And this is actually something that we do observe. So a practical solution to that is to normalize eta S to be a probability distribution over all of the state space, right? So it's not only how many times do we visit or what's the probability of visiting a specific state S, but what is the probability of visiting a specific state S relative to all of the other states. Okay? And indeed, this is what we're going to do next. We're going to normalize eta S to be a probability distribution. How do we do that? We simply normalize it by the sum of eta S's over all states, and of course this will result in a valid distribution. And we call this normalized eta S as mu of S. Why? I don't know. This this is just the notation that we use, and this is the same notation that you're going to see in the textbooks. The course's textbook. And so now we can redefine, and by the way, we know that eta s is proportional to mu of s, right? Because it's only a specific constant factor away from it, right? For a specific state. And so we can say that the gradient in J is proportional to the value defined through mu of s instead of eta of s. And this is fine. Specifically when we use gradient descent, we said that proportional values, proportional gradients are usually fine, just because they are commonly observed in the learning rate, right? We take gradient descent step, which are adjusted using the learning rate with a constant factor. In this case, the gradients are column vector of partial derivatives with respect to the components of theta, our tunable parameters.